Ricky's here. I saw him here.
I'm assuming Ricky's going to show up someday, but I marked him absent, so. All right. For the moment, we're going to talk about implicit differentiation again. We're going to work on some examples. My goal is I'm going to work through as many evens as I can get through. I posted the odd solutions, and the odds are the ones that are assigned. So my goal is to go through the process and talk through how each piece fits together, so we can make sure we have a firm understanding of how implicit differentiation works. For some of these problems, you can avoid implicit differentiation by rewriting the problem in a certain way, but many times it involves like using multiple rules in a lot of different combined ways, and it's oftentimes not as nice. So for example, in this first one, we will showcase afterwards how to rewrite this, but you'll find that it actually makes it a lot harder if you don't understand how to rewrite it properly. So let's talk about number 2. So as a reminder, implicit differentiation is defined as differentiating with more than one variable at a time. To do so, we're going to use d dx as our primary differentiation tool. Thus, we're going to take this x squared minus y squared equals 25. We're going to differentiate with respect to x both variables. Now, I'm going to start by distributing our d dx to each term. So d dx of x squared minus d dx of y squared equals d dx of 25. At this point, d dx stands for the derivative with respect to x. So for all x's and constants, this is the same as normal. The derivative of x squared is, of course, 2x. The derivative of 25 is, of course, 0. For this one, it is minus d dx of y squared. We are going to take the derivative as if this is an x, but at the end, we'll end up with a dy dx or y prime included as part of the derivative. So if I think of y squared like an x, the derivative of y squared would be 2y. But it'd be 2y with this dy dx attached to it, or y prime as we've called it. This represents the derivative of the function, meaning we end up with a solution that has a derivative currently in it. So how do we find the actual derivative? We need to get this component by itself. So using algebra rules, I'm going to start by actually adding 2y dy dx over. So we end up with 2x equals 2y dy dx. I'm going to divide both sides by 2y, getting the dy dx by itself. dy dx. You leave me with 2x over 2y. The 2's will cancel, meaning dy dx, or in other words, the derivative of this problem is simply x over y. Meaning, to find the slope of this function, I need to have both the x and y variables, or both the x and y values, so I can plug in, and it will tell me the slope for any point on this function. Briefly, let's compare this to if we had done this the traditional way by having y solved for. It is actually significantly tougher and yields the same results, just with a lot different components. Here we go. In this case, I'd want to get y by itself so I can take it rid of the standard methods. Well, to do so, I'm going to move the y squared over and the 25 over, which is going to look a little funny. X squared minus 25 equals y squared. The reason why this is annoying is because when I take the square root of both sides to get y by itself, I have to follow standard algebraic rules, which means I end up with 2 solutions, a positive and a negative. Now, in order to take the derivative of this function, I can't actually take it together. I have to now break this into 2 problems, the positive derivative and the negative derivative. So now I've taken one problem, broken into 2, and notice this derivative is a lot harder to do than the original derivative was. So this is why implicit differentiation is really helpful, because it can take a problem that would be nasty to do with standard derivative rules and allow you to solve it using implicit differentiation. Now the other nice thing is, if I want to know what the original is going to look like, there's a cool way I can do it. I now know what y is. If you want to know what y prime is, it'd be x over whatever y is. So in this case, plus or minus the square root of x squared minus 25. So again, it can still do it. It's just, again, one of these is significantly easier to work with. And now for this one, because I could end up with two possible solutions, I have to also take into account which one do I want. Because if it's a ellipse, if it's on top, I'm going to have a negative slope. If it's on bottom, I'm going to have a positive slope. It depends on how it's drawn, right? So if I look at the point, an x value that is right here, the top one should be the positive version because the top one in this location. The bottom one would be the negative version. I should end up with 2. And so this makes it very annoying and confusing about which one I'm supposed to get. How do I know which one? I have to have a picture more often than not. It's just so much fundamentally easier to deal with this version of the problem, which follows the same rules as if we dealt with it in terms of just x. So again, this is implicit differentiation. I chose to use dy dx because it asked me to. Dy dx can be annoying to write. I often write y prime instead because they're the same thing. However, if you have sloppy handwriting like I do sometimes, a lot of the times, then you may accidentally forget that it's y prime and think it's a y, therefore making algebraic mistakes. So I will often use dy dx just to make sure I don't make a silly mistake like forgetting to drop the prime. All right, this is number 2. The process is the same as if you're doing it with a standard function. It's just now when I take derivative of y, I will end up with a y prime every time as part of the problem. My goal becomes to get y prime by itself, so I make sure to isolate dy dx through algebraic steps until I have my solution. Number 4. Same process. Number 4 says x cubed plus y cubed equals 64. So again, I could, in theory, solve this one directly for y by subtracting the x cubed over and taking a cube root. Then I'm forced to do a chain rule problem, which is not hard. It's just a little tedious and time consuming. Instead, I'm going to do it by using our technique, implicit differentiation. Implicit differentiation just gives you another tool in your toolbox. This adds to our list of things, not replaces anything we could do. We can always go to this as an option if we choose to. We don't have to, though. I want to do ddx, which makes this become ddx of x cubed plus ddx of y cubed plus ddx of 64. So what this is asking is, how is the thing changing with respect to x? X cubed is changing with respect to 3x squared. Y cubed is changing with 3y squared to y dx. 64 is not changing at all, which is why it is a 0. Again, my goal is to get dy dx by itself, so I'm going to subtract 3x squared over, give me 3y squared dy dx equals negative 3x squared. I divide by 3y squared on both sides. I end up with dy over dx equals negative 3x squared over 3y squared. So the 3's cancel, leaving me with negative x squared over y squared as my dy dx. And again, if I had done this the other way, I would eventually get the exact same solution. It's just a little more tedious. Over here, I'd have to get y by itself, so I'd have to subtract the x cubed over, so I get 64 minus x cubed equals y cubed. Take a cube root of both sides. Y equals the cube root of 64 minus x cubed. We then have to do a power rule with a chain inside of it. The power rule would be 64 minus x cubed to the 1/3 power. We then would do the power rule, so y prime equals 1/3 times 64 minus x cubed to the negative 2/3 power times derivative of the inside. Derivative of the inside would be negative 3x squared. And as weird as it seems, 3's would cancel. On top, we end up with x squared. On bottom, we end up with the y squared. So it does work out in the end. And we will get the same solutions. It's just that one has a lot more components to it, as weird as that seems, because of how those variables fit together. Okay, let's talk about some basic rules for these implicit differentiation problems. Okay, d dx of any normal x's is like normal, so I'm just going to focus on the y's. So d dx of y is equal to dy dx. d dx of y squared is equal to 2y dy dx. Y cubed d dx of y cubed would be 3y squared dy dx. And the powers keep going like normal. Basically, you take the derivative like an x and then add it to y dx at the end of it. You can't express it any simpler than that. Let's look at number 6 to make sure we got that pretty solid. Now, because it's a separate variable, I have to follow all the rules from standard derivatives, meaning if I have something being multiplied, I have to follow the product rule. Something being divided, if there's an x on top and an x on bottom, I would have to do the quotient rule. If there's an x on top and a y on bottom, I still have to do the quotient rule because I'm still dividing something. Implicit differentiation will test how well you know these rules. So let's take a look at 64. X squared y plus y squared x equals -2. Let's take a derivative. Since this is a product, we're going to follow the standard product rule. Left d right plus right d left. But now that there's a y involved, I have to make sure to keep track of any time I take a derivative with respect to y, I have to end up with a dy dx. Here we go. Up here, d dx of our function. You'll notice that I'm showing the first step of distributing the d dx to all 4 components. You do not have to. You can just immediately start taking the derivative. I'm just using it to make sure to illustrate every step. d dx of x squared y plus d dx of y squared x equals d dx of -2. Okay, one side's easy. The derivative of a constant is always going to be 0. Let's look at the left-hand side. X squared y. So I got to do the product rule. So left d right plus right d left. So in this first grouping, my left is x squared. My left prime will be 2x. My right is y. My right prime will be dy dx. Here we go. The first piece, left d right plus right d left. Left d right, dy dx, plus right d left. So that is the derivative of the first term. Plus, second term, it has different lefts and rights, so I'm going to follow that through. So my left-hand piece is y squared, so its derivative would be 2y dy dx. My right-hand piece is x, its derivative would be just 1. Let's do it. So, left d right plus right d left. Beautiful. Now, my goal becomes to isolate dy dx, because that's the derivative. I have to follow all the algebra rules to make that happen. So I'm going to follow the standard algebra 1, algebra 2 techniques of get the dy dx terms on one side, everything else on the other, factor, divide. Here we go. Let's get the stuff that is not dy dx out of the way. So that's the 2xy and the y squared times 1. So that's going to become x squared dy dx plus 2xy dy dx equals negative 2xy minus y squared. Looks pretty good. Next thing we do, get all the dy's to factor out. So dy dx factors out, leaving behind x squared plus 2xy. Negative 2xy minus y squared. I then divide to get dy dx by itself. Dy dx is equal to negative 2xy minus y squared over x squared plus 2xy. And this is your derivative. This, number 6, is the first problem where it is almost impossible to find out what y is by itself. Well, on number 2 and number 4, we could do algebraic steps to isolate the y, move the terms over like we did, take a square root or a cube root to get y by itself. There is no good way to get y by itself because it is y in one term and y squared in the other term. Unless it happens to fit a certain factor form or some other component from algebra, there is no way to get y by itself, so therefore there's no way to take a standard derivative. Yet, we can take an implicit differentiation and still find the solution. Would you guys, we've seen how the derivatives. Do you want to see natural functions?
Yes.
You've probably never seen functions like this before. Because in algebra, we avoid these like the plague. This is the first time we're seeing real complex functions. Okay, so the first one was x squared minus y squared. Do you have these written down somewhere? Okay, good to see you. Just those first three, please.
Is that one? Is number 2 just a circle or?
It's, I believe, an ellipse. Because it's a minus instead of a plus.
Oh, okay.
I think. We'll find out in a second.
So just 2, 4, and 6?
Yep.
Alright.
And I got number 6 up here, so that should be good.
Alright.
Okay? Let's take a look, shall we? I have my web browser. Let's see. Business. Compound interest formula, very important.
Ah, yes. Oh, was it? That's one of your open meetings.
Okay. So the first one, it was x squared minus y squared equals 25.
Yep.
Ooh, look at that. Okay.
Oh, wow.
Yeah, so that makes it really important that this has both an x and y value, because if I just say x is 5, well, there's a 5 that's up here and the 5 that's down there. So I want to make sure my derivative contains a y value as well to know which x of 5 I should use. The second one, it was x cubed plus y cubed. X to the third plus y to the third. This one should also be pretty standard function. Equals, what was it?
64.
64, thanks. Look at that. That bad boy.
It's like a UFO.
It is a UFO. Can you not see Roswell, New Mexico right there?
Oh, yes.
Oh, this is so cool.
I know, right? Alright, this last one. You ready? Like I said, so far all of these could be solved manually, but you'll have to do some weird splitting. You have to also do more than one differentiation. This one cannot be split, so let's see what it looks like. It could be cool, it could be lame, who knows. Plus y squared x equals -2. Look at that. It's so pretty.
That's cool.
Right? So again, like it makes sense that it has to have an x and a y in the derivative because there's x and y's multiples of them for the same values. So like for my x's, if I go over here to x is 10, I can be talking about this x is 10 or that x is 10, which should have wildly different slopes.
Does it ever actually hit 0?
No.
Undefined on 0.
Undefined 0. And you can see that because if the x value is 0, you'd have 0 plus 0 equals negative 2. Same with the y. The y will also have an asymptote. When you start seeing these combinations, this immediately shoots a red flag that you have to do implicit differentiation. Again, as we've mentioned already once, and I will mention multiple times, because this seems like it's like this new thing, so I could use it a lot. It's like this should only be used when it's needed. The other rules are still applied. You can still use them at any point in time. We use them on multiple times in this problem. The idea, again, is that it opens up the door to more functions that we couldn't solve before. Implicit differentiation. Another, like 8. Another one that cannot be split very well. Would you like to see what this one looks like before we start?
Yeah.
Square root of xy equals x squared y plus 1. Square root of xy. Square root of xy equals x squared y plus 1. Not as fancy. I'm guessing that there's probably something I could do to get this to factor somehow. Ooh, what's that up there? It's doing something up there. So I'm guessing this has a big arc up here. Way up there. Okay. So let's do it. Square root of xy equals x squared y plus 1. Now, as I mentioned, and we'll keep mentioning, this is just a different technique. Its sole purpose is to increase the toolbox of derivatives we can do. Remember, we started with just the basic power rules. Then we started adding in things like the quotient and product and chain rules. Then we added in things like the ability to do trig functions. Now we've got to the point where we can actually take these weird complex functions with multiple y's, multiple x's, and we can still take a derivative and still find the slopes. So let's do it. Left-hand side I'm going to have to rewrite as xy to the 1/2 power equals x squared y plus 1. All right, we're going to do d dx. So derivative with respect to the x of the entire function. I should be through. That means I'm going to do d dx of the first piece, xy 1/2 power equals d dx of x squared y plus d dx of 1. Again, I know this thing's going to go away. I'm just going to mark it through and forget about it. Let's talk about each piece. The left-hand piece, xy. The chain? For sure. Definitely. What else? It's got a product in it too. Because it's x times y inside of it. So let's do the chain part first. How does the chain work? Beautiful. Then I need to multiply that by the derivative of the inside. The derivative of the inside is a product. So I got to do the product rule. My product would be left prime would be 1, right would be y, right prime would be dy dx. Okay, left d right plus right d left. Left, I'll put it in parentheses, d right, dy dx, plus right, d left. Equals x squared y. So in this case, my x squared y, that's another product. So I'm going to do a different product over here. My left is x squared. So my left prime would be 2x. My right would be y. My right prime would be dy dx. Beautiful. All right, so it equals left d right plus right d left. There's my equation. Now, this is the part that makes implicit differentiation frustrating. You can't get around it for a problem like number 8. And remember, my goal, long-term goal, is to get dy by itself. I have to do whatever is necessary to get all the dy dx's on one side and everything else on the other. Which means this will be one of the few times where I encourage you to FOIL through, redistribute terms. Like this is ones where you really have to have firm algebra skills. Because as of right now, I have dy dx on the left-hand side in a parentheses with another term that does not have dy dx. On the right-hand side, I have a dy dx as one of the two terms. I need to get them both on one side. Everything else on the other. What am I going to do?
You simplify on the left side?
Yes. By simplify, I hope you mean distribute. So I'm going to take this outside term and apply it to both of these. Now, how much will I simplify? Not much. I will simply multiply them through, and if something nice simplifies, I will take care of that. Otherwise, I will leave it there. Remember, my long-term goal will be, I just want dy by itself. Let's do it. So I distribute this to the first term. So that would be 1/2 x, y to the negative 1/2, dy dx. I took this outer term, multiplied to this term, 1/2 x, the square root is still there, the dy dx is still there, all the terms are still there. Plus y times this thing, so it'd be 1/2 y times that thing. So the left-hand side has been multiplied through. Nothing's happened on the right-hand side yet, so I'm just going to leave it equal to x squared dy dx, plus I'm going to put it in order 2xy. I recommend putting your dy dx's at the end of every statement, or every term. That way they stay there. All right, I need to get all my dy dx's on one side. Which side? Yes, one of the sides. Get it to one of the sides. And then I got to get everything else on the other side. So, next step.
Subtract the x squared dy dx and subtract the 1/2, like just swap it.
Yep. I'm going to swap these two using subtraction. So, 1/2 x, xy to the negative 1/2 dy dx minus x squared dy dx equals 2xy minus 1/2 y xy to the negative 1/2. Okay, so far so good. I want to get dy dx by itself. What do I do next? Factor it out. Dy dx comes out. So what's left behind? I have 1/2 x, xy to the negative 1/2 power minus x squared equals 2xy minus 1/2 y xy to the negative 1/2 power. You could be asking me, Douglas, in algebra, I would never accept a negative power. Yeah, in calculus, we don't want to do that. This problem's already bad enough. Leave it. It's okay. My high school teacher would say something incredibly sexist at this point. Don't be stupid. Okay? Yes, he was that way.
How's that right now? How's that second way?
You're thinking of a different insult. Dy dx. Then divide, you get dy dx by itself. It's going to be nasty. That's fine. Because Because all my goal is to get to y dx by itself. And there it is. Whatever steps are necessary to get to y dx by itself. That is the derivative of the original function. Square root of xy equals x squared y plus 1. And there's no better way to find it.
But you have to plot the negative 1/2 y and solve the negative 1/2 to get rid of the negative.
Yeah, I should. Am I going to? No. I'm leaving it right there. This is bad enough. And the thing is, if all I care about is eventually finding a slope of some kind, like let's say I wanted to find the slope at the specific value of, I don't know, is there a nice number anywhere on here? I think not. This one's pretty nasty. I don't think there is. If I wanted to find a specific value, let's say right there, I would just take this equation and grab a calculator and plug in the x value and the y value into that nasty formula and be like, thank you, calculator, for being my friend. The question you haven't asked yet is the one that should scare you the most. This is the first derivative. Would there ever come a time where I could do a second derivative this way? Yep. You better believe it. That's for next week. And we'll stick to primarily with simpler functions as this one to do that with. But it turns out the rules are the exact same. This is with the standard derivative. So, questions? We'll go tomorrow to work on some more. I'll have all of these to you on Monday at the end of class. If they're moving over the weekend, you can get started on them and then come in with any questions that we'll answer on Monday. Implicit differentiation. Yay! Yay! And if you look at your homework assignment, you'll notice that it contains questions from any standard derivative problem. Questions from, can you find the derivative, which is the first set. Can you find the derivative and evaluate at a specific point? So can you find the slope at these points? Can you find the slope of the tangent line at a specific point? And these have some pretty cool functions in here, which we're take a look at. The folium of Descartes is one of my favorites. The bifolium just looks weird. I don't know why. I always think of Mickey Mouse ears, but I know that's wrong. And again, just find the equation of a tangent line. So everything we did with the derivative, we now do with implicit differentiation as well. Can you find the derivative? Can you find the slope? Can you find the equation of a tangent line? So can you find y minus y1 equals m parentheses x minus x1? All those come in now. Yay! So we'll work on some more of these tomorrow. Personally, yesterday. That's beautiful. It's a star. It's the next. New solution. So, make sure you check your work as you go. If you're finding that you're constantly getting the wrong solution, make sure you come in and ask about it. I'll see you guys tomorrow. Bye, have you back, Michael. Stop recording.